Thanks for the introduction. My name is Ellen Schoeller, and I'm working with Schneider-Kreuznach as a product manager for the industrial optics. And my topic today is the wide spectrum of optical filters. So I give an overview of what filters can do and what is possible with them. A small overview over the content. So first we have a small introduction. Again, what is light and what is color as a basic understanding. And then we will have a short look into the definition of the optical filters, the working principle, and a very short term of terminology so that we all have the same language and will use the same words. And after that, we go into detail in what special filter types are there on the market available. And of course, also how are they connected to the lenses or the camera? So what mechanics is around. And after that, we will have a look into what happens when I combine a light source and a filter. So this connects to the beginning, what is light, what is color. So let's start. What is light? I think the most of you know light is electromagnetic radiation, and it can be understood as a wave. And a wave, of course, comes with a certain wavelength. And white light or sunlight, as we know, contains a lot of different wavelengths. And so the wavelength of a wave defines the color. We know this phenomenon from the nature. When we have a rainbow, it is caused by the sun, which is sending white light, but the rainbow is colored. So we know the sunlight, white light contains all different wavelengths. And to make the understanding easier, I showed the red light has longer wavelength than green light, or especially the blue light has the shortest wavelength. This is just to understand what we are talking about soon. And yeah, we see that in the overall spectrum, the visible light is only a short part of the electromagnetic spectrum. Shorter wavelengths than visible we call the ultraviolet light, and longer wavelengths behind the red, we call it the infrared light. And we can now have a look. What is a filter? A filter is normally a flat glass, or it can also be a foil. And the filter affects the wavelengths it transmits. And the wavelengths can be transmitted or absorbed, or some are reflected, or a filter can also change the orientation of a wave, so the polarization can be changed. A more detail in the working principle of filters. We have on the left-hand side, we have the interference filters. And on the right-hand side, we have the absorption filter. First, have a look into the interference filters. They, when we have the incoming white light, so we have the glass here, and the glass for an interference filter is coated with thin film coats, thin film layers. And these layers let only one wavelengths pass, and all the other wavelengths included in the white light are reflected. And the other way a filter can work is an absorption filter, which is normally a colored glass, no thin film coatings here, just a color glass. And also we have a lot of wavelengths coming in, like white light, it's containing all the colors, and only one wavelength is able to pass these filters. So the result behind is the same, but with an interference filters, the unwanted light is reflected, and with an absorption or colored filter, the unwanted light is absorbed. So this is the difference behind, but the result is the same. And then, as I mentioned, a short look into keywords. So we see a typical transmission curve of a filter here. We have the wavelength at the bottom and the transmission in percentage on the left. And when the transmission is nearly zero, we talk about this is the blocking area. And when the transmission opens up over 90%, then we talk about the transmission area. And we define this transmission area with the wavelength where the transmission reaches the 50%, when it's coming from blocking, going to transmission, when it reaches the 50%, we call these wavelengths the cut-on wavelength. And on the other side, when it's coming from transmission and going down to the blocking, where it reaches the 50% transmission, we call these the cut-off wavelength. So between the cut-on and the cut-off, there is the bandwidth of the filter. So these are the main basic keywords when we talk about filters. And with that, we can now have a look into special filter types. I first want to talk about the short pass filters. And as you maybe might guess, the name always describes the working principle. So short pass means short wavelengths can pass and the longer wavelengths are blocked. So these filters blocks, of course, the infrared light and the visible parts of the visible light, and maybe the UV can pass these filters. So a short pass filter is used when you want to block unwanted infrared light, maybe caused from your light source or your sun, or when you have heat radiation you want to block, you can use a short pass filter, for example, in 3D measurement, of course, or security applications, or when you have heat, hot processes to monitor, like combustion monitoring. Yeah. Then we can have a look to the opposite way of a filter. We have a long pass filter. So these filters let the long wavelengths pass and the shorter wavelengths are blocked, which means especially UV light is blocked and parts of the visible light and infrared light can pass these filters. This is these filters, long pass filters, can be used maybe for food inspection or in traffic applications, of course, in 3D measurement or in medical applications. There's a wide spectrum, I would say, where you could use long pass filters. And then we will have a look into what happens when you combine a short pass and a long pass filter. We call it then a band pass filter, which means we have a blocking part on the left and we have a blocking part on the right, and in between these two blocking parts there's a transmission part and wavelength interval which where the light can pass the filter. So it is, these filters are used to select bandwidths of wavelengths. When this bandwidth gets very small, we call this a narrow band pass filter. This is why I wrote this also on the top. Band pass filters are mostly used for spectroscopy applications, or when you have light sources with small bandwidth spectrum, you can make sure that only the light of the light source is coming to your system, and all the other light which might be around from the sun or other illumination is blocked. So this is mainly used for bioanalytics or medical parts, but also used in traffic and, of course, always 3D measurement applications. One more group of filters are the neutral density filters. Those filters have a constant transmission curve. So this means they reduce the light intensity in general. Over all wavelength, they just reduce the light intensity. And this might be interesting when you have applications where you have a lot of light, which is too bright for your camera or lens system, and you're not able to go down with the exposure time of the camera anymore, or you're not able to close the aperture of the lens further. You can use a neutral density filter to reduce the amount of light in general. So it is perfect when you want to watch bright scenes. And the neutral density filters, so there are several types of, with several transmission values. So I would say the lightest one is when we have 25% transmission, and the heaviest one for really bright scenes is really almost down to zero, but not really zero. So that is really blocking the light and reducing the amount of light. One main specification for these filters is that they do not change the color. So all wavelengths are reduced by the same, so the transmission curve is very constant. And one more type of filters are the polarizers. These are a little special, and we need to know that light normally is not orientated, so all the waves are doing in chaos, I would say. And with a polarizer, you can choose one direction of the light, and these phenomenon is very great to suppress and reduce your reflections. You know, these from consumer photography, when you want to take a picture of the sea or a lake and you have reflections on the water, but you can also use this in industrial applications when you maybe want to read a barcode on a metal part, and this is not readable for the camera because there are reflection. You can use a polarizer and reduce or suppress the reflection and easily read the code behind. But of course, application markets are, yeah. You can also use traffic or security or 3D projection. So there's a big part where you can use polarizing filters. And now we can talk about how the filters are connected to the camera. So, or the lens. Normally, the filters are screwed into the front of the lens. So the filter glass is mounted into a holder, which has a thread that fits the front of the lens. Or also sometimes it is necessary to place the filter between the lens and the camera. There is the filter glass mounted into a C-mount, which is a common thread of the lens and the camera. So this can be placed in between. And of course, for the polarizing filters, it is necessary that the holder is fixed to the lens, but the glass, the filter glass, keeps freely turnable so that you can choose the orientation you want. So there are several mounts that are available to put your filter to the lens or to the camera. Standard thicknesses of the glass is normally 2 millimeters, but there are some applications where it might be useful to only have 1 millimeter. which is more and more common. And when we talk about filter glass, of course, you can always get your filter as an unmounted filter glass, as I said, with 2 millimeters thickness or maybe 1 millimeter thickness. And out of these glasses can be cut of any shape you would like to imagine and maybe fit your application best, like rounded edges, triangle, elliptical things, or whatever your application might need, you can cut out of a single glass. And then, as I said, I wanted to have a short look why it is important to check that the light source and the filter match each other. And on the left-hand side, we have a spectrum of a light source. This should be a typical spectrum, like from an LED or so. In the middle, we have the transmission curve of the filter. And on the right, we always have the result when we combine these two. And we have the top row, you see the filter transmission might perfectly fit the spectrum of the light source, but in combination, you see there's immense loss of light when you combine a filter like that with a light source like that. So when we have the same light source with a filter with very steep slopes and a constant plateau of transmission and a steep slope on the other side, we see that all the light that is coming from the light source is transmitted perfectly as we want to see it, like this. So just keep in mind what is useful filter transmission curve and what is looking useful, but your result might be bad. So with this, I want to thank you for your attention. And of course, you see my all my contact data if you want to get in contact with me, and hope we have some time left for some questions, or we do this in the big Q&A afterwards.
We have some time left. So there's a question about, is a ruggedization of filters possible?
Yes, of course, a ruggedization is possible. Normally, the filters are only fixed with a screwing ring, which is the standard mount type, but of course, a filter can also be glued into, and no screwing ring is needed, or you can use both glue and screwing ring. Of course, ruggedization of filter is possible.
And can filters be combined?
Yes, this is also a nice question. Of course, filters can be combined. When you might notice that your fitting bandpass is not in the portfolio of your filter supplier, you can just have a look of if there is maybe a short pass and a long pass that you can combine to get out your personalized bandpass, I would say. And most of the filters are also stackable, so you don't need special mounts to combine them. Just screw them into the other, and you have your own bandpass created.